Okay. Actually, the measure by which you can consider a system that is chaotic, that is Lyapunov exponent. Yes. The till now not so. If you see the Kaplan-York dimension in this regard, then for hyperchaos the dimension is more higher. So if you get two positive Lyapunov exponents simultaneously, then you can say hyperchaos is come to play. Okay. So yesterday we learned how to analyze the stability, and numerical part will be done in some tutorial. Today I shall introduce the physical time delay system. How can you design a time delay system using electronic circuit elements? Okay. So first of all, what is delay? Suppose you have a time series of a signal, let it sinusoidal. Suppose it is X. Then if there is delay, then the delayed signal somehow will look like this one. Okay. So this amount of, suppose this amount, this corresponds to delay. So we have to implement some circuit, mainly electronic elements, to incorporate this type of delay. So in literature, one familiar delay element is LCL block. What is LCL? L means inductor, C means capacitor, and L means inductor. So these are L and here C. Grounded. This block can provide you time delay as desired. It has the transfer function T of S is equal to 1 divided by 1 plus LC into S square. It has some merit and some demerits. Merit, easy. It is easy to design. Just connect L and C in this way, and you can get time delay effect. But demerits, there are a lot of demerits of this. First of all, this element, what type of element, active or passive? L and C. Anyone from physics background? Inductor, passive element. It cannot generate energy. Okay. Capacitor is such. So if I pass a signal through a passive element, then attenuation occurs. So first of all, attenuation. Second one is the system is very bulgy. If you want to make an inductor, then you have to wind some wear. Okay. So second demerit is voluminous. Third one is very intricate. This is actually a low pass filter. Okay. This is actually a low pass filter. And owing to its low pass filter property, it restricts the higher frequencies. So if you want to get chaos, then the higher portion of the frequency will cut, and you will not get chaos to that extent. So after considering these demerits, we considered all pass filter or APF as delay element or delay block. What does it look like? Obviously, active all pass filter. So the circuit looks like this one is an operational amplifier or op amp. Suppose these are R1, R2, R, and C. Here another demerits is of LCL block. If you want to change the value of the delay, then you have to change either L or C. The variation of L and C is very difficult. Okay, so you cannot that smoothly vary that system. But here we keep a potentiometer in place of R. By potentiometer, you can vary the resistance. So you can get the variable delay effect. So let us analyze. Suppose in this direction a current flows I, and in this direction another current flows I. Here is the voltage V, here suppose VI and V0. So first consider this branch current. So considering this branch, we get, suppose this one is 1 and this is 2. In one branch, there is VI minus V divided by R1 is equal to V minus V0 divided by R2. It eventually gives V0 is equal to V1 minus R2 by R1 minus R2 by R1 VI. Suppose this is number 1, and consider the equation in second branch. Here I1 current and I2 current. So here you can get V is equal to VI divided by 1 by CS, R CS into 1 by CS. So VI divided by so substitute V from 2 into 1 and you will get something like this. V0 is equal to 1 divided by R plus 1 by CR into 1 plus R2 by R1 VI minus R2 by R1 VI. And if you do some steps, then you can get V0 by VI is equal to minus of R2 by R1 into S minus 1 by CR R1 by R2 divided by S plus 1 by CR. So this reads minus R2 by R1 S minus R1 by R2, suppose omega 0 S plus omega 0, where omega 0 is equal to 1 by CR. So the transfer function becomes transfer function becomes T of S is equal to minus R2 by R1 S minus R1 by R2 omega 0 divided by S plus omega 0. So in general, we can write it minus of A1 S plus S minus omega 0 divided by S plus omega 0. So this is the transfer function of the all pass filter. What are the advantages? Advantages is, first of all, this is active element, and if we feed any signal, then it will not get attenuated. You can get the same signal, and the variation of delay may be continuous by simply varying the resistance R. Also, as it is all pass filter, it passes almost all frequencies limited up to the bandwidth of the op amp. Obviously, that is physical limitation, but that is more than LCL block. And you can design this in IC very easily because there are only op amp resistance and capacitance are employed. So equipped with this, we can consider the electronic circuit idea. So what was our equation? X dot is equal to minus AX plus B Fx means minus Nx plus M tan hyperbolic Lx. Actually, this one is tau. So I have to design some blocks like tan hyperbolic block and a simple linear block, and then I have to pass it through some filter. So the idea here becomes first of all, this number one block, here we shall design f of Vt. See, here I have transformed the x to Vt because I shall be working with voltage. Then I shall give a second block, that is gain. Then third one, I shall provide an inverter. We invert the signal. Then I can do this like of arrangement, a switch, and then low pass filter section, and then some buffer, and then delay block. Then also I can employ some buffer and feed it to F. So in this portion, you can get from here V of t that mimics the X. So if we come to the more rigorous circuit, so the F tau block becomes like that. Here you can get the tan hyperbolic option. Okay. Next, I am feeding it to another one. Ground it. This one R1, R2, this one R3, and bring this one R4, R5, here R6, another op amp, R7, this provides actually the gain. Now the inverter, are 9, and here we get f of v tau, and from here you can get minus f of v tau. Here we can arrange a switch and a low pass section. Now we can design buffer using op amps. Just suppose it is B, and here we are giving the delay element that circuit. Okay, another buffer and feeding to this. So this portion actually is number one there. This one is gain, number 2. This one number 3, number 4, 5, 6, 7. This one number 3, this one number 4, this one 5, this one 6, and this one 7. So if we write the equation of this system, then we can get R0 C0 dV of t dt is equal to minus V of t plus minus, depending upon the position of this switch. If it comes here, then plus. If it comes here, then it is minus. So plus minus Bf of Vt minus Td, where f of Vt minus Td, it reads R5 by R4. See this portion, R5 by R4, Vt minus Td plus R5 by R3, beta V saturation, tan hyperbolic, omega R2 by R1, Vt minus Td divided by Vsat. Now we want to dimensionalize. For this, we consider T is equal to T divided by R0 C0. Tau is equal to Td divided by R0 C0. X is equal to V of t divided by Vsat. X of tau is equal to Vt minus Td by Vsat. And R5 by R4 is equal to N1. Beta R5 by R3 is equal to M1. And omega R2 by R1 is equal to L1. Then substituting these in this equation, you can get x dot is equal to minus x plus minus b minus n1 x tau plus m1 tan hyperbolic L1 x tau. So this is our equation from electronic circuit, and you can mimic all the scenarios you obtain numerically or analytically. Any question up to this? Anything do you want to be clarified? Yes, obviously. Yes. Output voltage will be beyond the saturation. Yes. Obviously, actually what happens to tan hyperbolic graph? Something like this. In op amp also we can get something like this, Yes, obviously. This is V saturation voltage and we have normalized that with V sat. You can see that. Okay. So by this way, we have obtained the tan hyperbolic effect and another minus X effect. And these two actually generates a nonlinearity like this. That is necessary for our present system. Okay. So this is the time delay realization of time delayed system in electronic circuits. You can see the numerical scenarios appearing here. Now the second portion comes, though these are not related to tipping, but actually these are the idea how to handle time delayed system to incorporate to some ecological models. Okay. Now next question comes, collective behavior of time delayed system. So what happens if we connect more than one system to some connection topology? Okay. Here also we consider x dot is equal to minus ax plus b of x tau. X may be any function you can consider. Now we consider an unidirectional nonlinear time delayed coupling. It is actually driver response coupling. So the driver is this system and the response is y dot is equal to minus ay. Suppose it is b1 and it is b2, f of y tau 1 plus b3 x tau 2. So here two types of delay are employed. One is tau 1, that is inherent delay, that is into the system, and another is coupling delay. So what we have done, this one is driver system and this one is response system. We have applied some non-linearity and delay tau 2. Here tau 1, here tau 2. Here the constant b1, b2 and here b3. So this type of coupling can make some interesting coupled behavior relating to synchronization. In the chaotic and hyperchaotic regime. So the synchronization reads, if we want to consider the stability of the synchronization, then we have to follow some steps, some stability analysis. Suppose these are somehow synchronized. So the synchronized manifold will be given by synchronized manifold will be given by x of tau 2 minus tau 1 is equal to y, where x of tau 2 minus tau 1 is equal to x of t minus tau 2 minus tau 1. Okay. So if this happens, then we can say that the driver and response system synchronized. Let us define error. So we define error tau a sigma delta is equal to x of tau 2 minus tau 1 minus y. Suppose this one is 1, this one is 2, and this one 3, and this one 4. So when delta becomes 0, that means synchronization. If that doesn't happen, then synchronization doesn't happen. Now, depending upon tau 1 and tau 2, there are mainly 3 cases. Number 1 is anticipatory. Anticipatory synchronization, or we call it AS. When tau 2 is less than tau 1, then we can get y is equal to x of tau 2 minus tau 1 is equal to x of t minus tau 2 minus tau 1. This one is negative. So y is equal to x of t minus plus tau. That means the state of the response anticipates the state of the driver. Okay, so how can you get? So suppose this one the state of the driver, and actually it anticipates, the response state anticipates. This one is driver and this one is response. So this is anticipatory synchronization. If these two are same, tau 1 is equal to tau 2, then you can get complete synchronization or CS. In that case, y is equal to x. You can see that these are same and no delayed effect is there. So here you can get complete synchronization. And number 3, there is lag synchronization or LS, where tau 2 is greater than tau 1. In that case, y is equal to x of t minus tau, tau greater than 0. Tau means tau 2 minus tau 1. So here what happens? The response lags the driver. Suppose this is driver and it lags. The response lags the driver. So these 3 kinds of scenarios we can obtain from this type of coupling. For another coupling, you can get other type of synchronization scenarios, but presently we are interested in this type of coupling. Now let us check what is the condition for this synchronization. From equation 4, we can see that y of t minus tau 1 is equal to x of t minus tau 2 minus tau 1 minus tau 1 minus delta t minus tau 1. And y tau 1 becomes x of tau 2 minus delta of tau 1. Suppose this is 5. Now, the dynamics of the error equation, if I want to check what the error is with respect to time, we have to take derivative of this. So delta dot actually becomes x tau 2 minus tau 1 dot minus y dot. This is 6. And if we substitute these in equation 2, then we can get from 2, then we can get x tau 2 minus tau 1 dot is equal to minus ax tau 2 minus tau 1 plus b1 f of x tau 2. And eventually delta dot reads minus ax tau 2 minus tau 1 plus b1 f of x tau 2 plus ay minus b2 f of y tau 1 minus b3 f of x tau 2. I just included the values of x tau 2 minus tau 1 and y tau 1. Now, if I put this, we just obtained from here, then we can get delta dot is equal to minus of a x of tau 2 minus tau 1 minus of y plus b1 minus b3 into f of x tau 2 minus b2 f of x tau 2 minus delta tau 1. Now you can expand it in Taylor series, and if you expand, then you can get minus a delta plus b1 minus b3 f of x of tau 2 minus b2 f of x of tau 2 minus delta f prime x of tau 2. Here Taylor series is applied. So finally you can get minus a delta plus b1 minus b2 minus b3 into f of x tau 2 plus b2 f prime x tau 2 delta tau 1. Now this is inhomogeneous equation and you cannot go further with this equation. But if we make this term to 0, then we can do some calculation further. So we give the constraint b2 plus b3. With this, the equation becomes delta is equal to minus a delta plus b2 f prime x tau 2 delta tau 1. This is 8. Now here comes the Krasovsky-Lyapunov theorem. For positive functional. They have defined a functional that is called v of t is equal to half delta square plus mu minus tau 1 to 0 delta square t plus phi d phi, where mu greater than 0, any arbitrary parameter, positive parameter. So if we can show that the derivative of the functional is negative along the origin of this, then we can say the origin is stable and the synchronization is stable. Okay, so do that. We are doing v dot is equal to actually delta dot plus mu delta square minus mu delta tau 1 square. Substitute the value of delta 1 from here, delta dot from here, delta minus a delta plus b2 f prime x tau 2 delta tau 1 plus mu delta square minus mu delta tau 1 square. It reads minus a delta square plus b2 f prime x tau 2 delta tau 1 plus mu delta square minus mu delta tau 1 square. This one is 10. Now right hand side of this must be negative to have the synchronization stable. So we can write it as v dot is equal to minus mu delta square as common part, a minus mu divided by mu minus b2 f prime x tau 2 divided by mu delta tau 1 by delta plus delta tau 1 square divided by delta square. Now we assume minus delta square a minus mu divided by mu minus b2 f prime x tau 2 divided by mu. Suppose this one is x plus x square. We are considering this as x is equal to minus mu delta square. Suppose this is a function of gamma, x and mu. This one is suppose 11. So this function we considered as gamma and x is equal to that. So v dot is negative if gamma x mu minimum value is greater than 0. To find the minimum value of gamma, we have to just derivative it, and we find d gamma x mu with respect to dx is equal to 0, which eventually gives x is equal to b2 f prime x tau 2 divided by mu. And substituting this in gamma, gamma mean reads 4 mu a minus mu minus b2 square f prime square x of tau 2 divided by 4 of mu square. Suppose this one 12. Now the condition of stability. Condition of stability, what that read, gamma mean greater than 0, that is a is greater than b2 square f prime square x of tau 2 divided by 4 mu plus mu. Now, if you can remind that we said that mu is greater than 0 and any arbitrary parameter. So we have to find the mu value. Okay. For that, we shall consider that phi of mu is equal to this one, b2 square f prime square x of tau 2 divided by 4 mu plus mu. Now minimize it. D phi d mu is equal to 0. This gives mu is equal to modulus of b2 f prime x of tau 2 divided by 2, as mu is positive. Mu is greater than 0. So with this value, we can get phi minimum value is equal to mod of b2 f prime x of tau 2. If we substitute this here, then we can get condition for stable synchronization. Condition for stable synchronization that reads A is greater than mod of b2 f prime x of tau 2. If this condition is valid, then depending upon the values of tau, you can get anticipatory, complete, or lag type of synchronization. So this one was just one type of coupling. If we consider another type of coupling, suppose we are considering mean field coupling. The equation may be given as xi dot is equal to h of xi tau I and some parameter p plus epsilon qx bar minus xi, where x bar is equal to 1 by n summation over j is equal to 1 to n xj. That is, the mean field coupling is applied here. If you go through the similar type of analysis, then you can apply the Krasovsky-Lyapunov theorem, and in this case you may get some generalized anticipatory synchronization and generalized lag type of synchronization. The synchronization is not the same but follows the driver or follows the system in some generalized way. That means between the systems there are some functional form. Okay, and depending upon epsilon and q, the system may show amplitude depth or AD states. That is, two oscillators were oscillating synchronized way, but if we provide some specific values of epsilon and q, then oscillation just dies, and you can get amplitude depth case. Up to there, any question? Yes, obviously. That V function, that is you can get some papers or books from where you can find the Krasovsky-Lyapunov theorem. They have given some theorem, and from that theorem we consider a positive functional like that, positive definite functional like that. So positive definite functional, it must be negative along the trajectory of the error equation, and that may give rise to the synchronization condition for stable synchronization. Okay, this is a bit of off topic to you because this is a tipping point workshop, but these are the tools for time delayed system, and you have to learn the tools to employ the time delay in your system if time delay comes. Okay, so this portion is enough. Now I shall show you a model where Visu effect of time delay, effect of time delay in ecology. First of all, let me consider the Lotka-Volterra equation. You know the Lotka-Volterra equation. I think all of you know. Yes. So what happens if there are prey and predator in some place, some jungle, etc. Then suppose prey is expressed as X. If there is no predator, then X will grow. Suppose the resources are full, okay, then we can model it AX, the simplest model. So it will grow. And suppose Y is the population of predator, and if there is no prey, then what happens? It actually decays. The predator dies, being deprived of food. But if in a jungle you leave these two, predator and prey, then there are some interactions. So that interaction here plus BXY and CXY. So this gives rise to the well-known model Lotka-Volterra. And there are periodic oscillation in this model, you know. But actually, if you want to see the idea that there are some time delay between the interaction of predator and prey. So if you want to model this with time delay system, so if we try to incorporate time delay here, then we have the equation. Suppose we are omitting X and including the logistic equation. So A1, 1 minus X by P into X minus B1 Yx, and Y dot is equal to minus AY plus B2 X of T minus sometime tau, Y of T minus sometime tau. Here you may include the time delay, and the inclusion of delay incorporates many difficulties to system, but the difficult the system, the more realistic is the system. Okay, so in a paper, Visu, Guttal considered the population dynamics Noi, Mair and May from this paper, the model of population dynamics. Population dynamics under grazing effect. They have considered a first order model of the form dv of t dt is equal to r v of t 1 minus v of t minus tau divided by k plus c plus sigma c eta c of t v of t square divided by v of t square plus v0 square plus sigma v eta v t, where v of t is population density, r is growth rate, k is carrying capacity, tau is time delay, c is maximum grazing rate, v0 biomass at which the grazing result is half, sigma c is standard deviation of fluctuation of maximum grazing rate, sigma v standard deviation for additive external fluctuation, and eta c uncorrelated Gaussian noise. By considering this model, they have obtained some interesting results. If you draw V versus C, then it shows something like this. This is stable and this is bistable zone. For certain values, 0 less than tau less than 1.4. But if the delay increases to some extent, then the figure shows some interesting behavior, C and V here. Is a dotted line, and here in this zone, you can see oscillation. This is for tau greater than 1.4 case. The details you may find in the paper of Vishwesha Guttal in 2013. I don't know very much about tipping point because my work doesn't contain tipping point, but I have introduced you with time delay and equipped you how to consider and how to analyze the time delay system. And in next tutorial, I shall show you how to solve time delay differential equations using 3 mainly packages. One is C++, it is not package but language. Second is Python. And third is XPPAUT. So the idea will be clear of infinite dimensionality, how it comes, and that will be full-fledged. Okay, any question? Okay. Tau. Yes, obviously. Obviously. Physically means in ecology, you can consider a system is happening just now, but it had some consequence previous back. Okay, so that portion is included in the time delay. You may consider the book of Kuang for more detailed part. I just showed you the example here. Okay, so those relation between suppose hare and fox, that is not actually instantaneous, that has some previous delay effect or history effect. If you want to do the model precisely, otherwise you can do the instantaneous modeling or ODE modeling. Okay. 1.4. See, the graph was drawn with respect to grazing rate, but the delay have finite effect. This time delay, this delay range. If the delay is increased, then you can get oscillation and many more interesting behavior there. You may refer to the paper. In this paper, not now. Any other question? I think it is a little bit different topic to you, but it's not so complicated. If you try, you can get many interesting results using time delay. This one and this one? That one and that one? No. These are different model. I just showed the example from the paper of Biswas. Okay. I don't know about tipping point, so I am not going to tipping point case. I just showed you the tools and formalism, how the time delay may be handled. It was a little bit of mathematical, I think. Any further question? Okay. So I am stopping here. Thank you.